Welcome back to the channel. Let's talk about the shallow water effects. A ship's behavior fundamentally changes when the water depth, or H, becomes a critical factor, typically defined as any depth less than about 1.5 to 2 times the vessel's draft, or T. The biggest impact is on the flow of water around the hull. In deep water, displaced water flows easily in all directions. In shallow water, the flow is heavily restricted between the ship's bottom and the seabed. This restriction forces the water to accelerate, creating 3 major linked effects: increased resistance, the squat effect, and altered maneuverability. First, let's discuss resistance. As water flow is constrained, the vessel experiences increased drag, requiring significantly more power to maintain the same speed or forcing the ship to slow down. It's like sailing through treacle. For the same engine setting, a ship's speed will invariably decrease as the water becomes shallower. This increase in drag also means that for any given speed, the required engine power can increase by as much as 50%. Second, and perhaps most critically, is the squat effect, which we've discussed before. The accelerated flow of water under the hull creates an area of lower pressure, effectively sucking the ship down closer to the seabed. This bodily sinkage, coupled with a change in trim, often causing the ship to sink more at the stern or bow, is directly proportional to the square of the ship's speed. This can dangerously reduce the under-keel clearance, or UKC, increasing the risk of grounding. Mariners must dramatically reduce speed to counteract squat, often moving at half speed or less in critical areas. Third is the impact on maneuverability. Shallow water fundamentally changes a ship's handling. When a vessel turns, it needs space for the water flow to generate the turning forces. This flow is stifled in shallow water, making the rudder less effective. Consequently, the turning circle diameter increases, and the ship becomes sluggish to respond to steering inputs. Compounding this, the vessel's directional stability improves, meaning it wants to stick rigidly to a straight course. While this sounds good, it means the ship is much slower to initiate a turn, but once it starts, it's harder to stop. Furthermore, the stopping distance is slightly reduced due to the increased hydrodynamic drag acting on the hull. All of these effects work together. A captain must be prepared to handle a ship that is moving slower, is closer to the bottom, requires significantly more power to maneuver, and responds more slowly to the helm. Safe transit through shallow water is about respecting the powerful hydrodynamics at play. If you found this video helpful, please give us a thumbs up, hit the notification bell, comment, like, share, and subscribe for more insights. Thank you.